Okay, the last type of problem we can see that will work with the kinematic equations is an object on an incline. So something maybe rolling down a hill or rolling up a hill, but it needs to be straight. So the hill itself needs to be straight. It could be a kid going down a slide. Now, the equation we're going to use right now is going to ignore friction for now. When we get into the next chapters, we'll include friction into the picture. But for now, we're going to say our incline is frictionless. There's no friction between the object and the incline itself. Okay? Oh, let's see. I'll just call it theta for now. Make it generic. Okay. Now, what makes the object go down the incline in the first place? Gravity. Gravity is trying to pull it down to the lowest point it can come to. But the incline's in the way, and so that does not allow the object to fall at 9.8 meters per second squared. It doesn't allow it to accelerate at the acceleration of gravity. That's what gravity's trying to do, is trying to give it an acceleration of 9.8 meters per second squared. But it can't because the incline's in the way. What we have to do is, with vectors, we're going to talk a lot more about vectors on Monday, but with vectors, you can break down a vector into what we call components. We can break down this vector into a piece that's parallel to the incline and a piece that's perpendicular to the incline. Okay? However you break it down, though, those two pieces have to meet at right angles, and they have to complete a triangle. So I can draw this piece over here, so that these guys meet at a right angle, or I can draw this piece over here, so that they meet at a right angle. The components, we call those components. The components always have to meet up at a right angle. Okay? This piece that's parallel to the incline, that's going to be the actual acceleration of the car. The piece that's perpendicular to the incline is not going to affect the car's overall motion because the incline's in the way. So only the piece parallel to the incline is what we want to know. Now, we have a nice right triangle. We know this middle blue line, that's the hypotenuse. We know it has a value of 9.8 meters per second squared. If we know where this angle is up here, then we'll be able to figure out in the size we want. Okay? All right. To figure out the angle, our traditional coordinate system has the y-axis vertical and the x-axis horizontal. That's our traditional coordinate system. But I could certainly draw a coordinate system that makes down the incline. Let me do it a different color here. Makes down the incline the x-axis, and perpendicular to the incline, the y-axis. You okay with that? How far do I have to rotate the axis to make that happen? Whatever theta happens to be. So our angle right here is theta. The y-axis has to move by theta to line up with that line perpendicular. So here's a triangle. I have the side that's perpendicular to the incline, I have the side that's parallel to the incline, I have the hypotenuse. The hypotenuse is 9.8 meters per second squared. I want the side parallel to the incline, because that's what the actual acceleration of this object will be. If I have the hypotenuse and the side opposite my angle, louder, sine. the sine of that angle is going to be this side. I'm just going to call it A for our acceleration. It'll be A over the 9.8 meters per second squared. That means our acceleration, A, is 9.8 meters per second squared times the sine of our angle. Now, whether we call it plus or minus depends upon how we define our coordinate system. For example, if we use that tilted coordinate system so that the x-axis is along the incline, down the incline, just according to a traditional coordinate system, would be positive. So our acceleration, that piece of the acceleration is pointing down the incline. So this acceleration would be positive, 9.8 meters per second squared. So the positive or negative sign just depends upon what you want to call your positive or negative direction.